Thus, we have derived the following equation for the geodesic in Schwarzschild spacetime. dr over ds squared is E divided by m squared minus 1 minus rg divided by r, 1 plus L squared over T 2m, no 2, m squared times r squared, no 2. Where E is energy and L is angular momentum. One should have in mind that this equation is applicable only for r greater than rg because we are using Schwarzschild coordinates, and if one wants to derive geodesics below the horizon, under the horizon, one has to use a different coordinate system which is not singular at the horizon. That's one should bear in mind. Now we want to use this equation to start with. We want to show some of the statements that we have made during the previous lectures. For example, let us consider radial infall of a massive particle to the black hole. So mass is not 0, but because we have a radial motion, L is equal to 0, angular momentum is equal to 0. So this equation simplifies to dr over ds squared equal to E over m squared minus 1 minus rg divided by r. So without loss of generality, we want to consider the following situation, that as r goes to infinity, dr over ds goes to 0. So it means that particle started its free fall at infinity with 0 velocity. So from this equation, this goes to 0 as r goes to infinity, as r goes to infinity, which means that from this fact, it means that E is equal to m. So the energy of the particle is just equal to its mass. As a result, this equation, this is 1, so this equation is simplified to the following one. So without loss of generality, we can consider this kind of motion. Of course, if energy is not equal to 1, so the particle started its motion with non-zero velocity at infinity, none of the conclusions that we're going to make is going to change. So, in the circumstances that we consider, the equation is very simple. So now we want to solve it to find how much proper time it takes for a particle. So our goal now is to find how much proper time, how much of the proper time it takes for a particle to free fall from the radius r big to the horizon, to r equals to rg. So then from this equation we can find that proper time necessary to do this free fall is equal to 1 to minus rg r over rg 1/2 dr. So taking this integral, we find this time to be, so this is a continuation of this formula, 2rg divided by by 3 r over rg 3/2 minus 1. So it takes finite proper time to make this free fall, as we promised in the previous lecture. Yeah, here the minus sign is present because for the free fall down the black hole, dr is less than 0, so the radius is decreasing, while ds is greater than 0. So as the time increases, radius decreases. That's the reason we have minus sign here. So here taking square root, we can have two signs. So we took the minus sign. So at the same time, from the fact that, remember that we have conservation law, that 1 minus rg divided by r dt over ds is equal to E divided by m. In our case, this is 1. So as a result, we have the following relation. We have a relation between coordinate time and the proper time in the Schwarzschild spacetime. And using this and this, we can find that dr over dt is equal to minus rg over r 1/2 1 minus rg over r. The minus sign again here for the same reason as minus sign here. Now from this expression we can find how much coordinate time t it takes for a particle to make free fall from a radius r to a radius very close at the horizon. Very close to the horizon. So it's not rg, but some vicinity of the horizon. Epsilon is very small. So then, coordinate time necessary to fall from the radius r to this rg plus epsilon, as epsilon, so first of all, this is just by definition is minus rg plus epsilon, r divided by rg 1/2 r dr r minus rg. So one can see that as epsilon goes to 0, the leading contribution to this integral is proportional to rg times log r divided by epsilon. So the time goes to infinity as epsilon goes to 0. So it takes infinite time, coordinate time, for a particle to fall from the radius r to the vicinity of the horizon. That was observed during the previous lecture, but for more generic situation, because it's not only the Schwarzschild observers which measure this time do not see body crossing the horizon. Any observer which stays outside of the Schwarzschild horizon never sees anything crossing the horizon, as we explained on the Penrose diagrams during the previous lecture.